You ever get that feeling your computer could be doing more? Working faster, even when it's brand new? Well, guess what? You're not wrong. Most of the time, we're leaving a massive amount of processing power just sitting on the table, totally unused. Today, we're going to look at a really cool tool called OpenMP that helps us unleash our CPU's full hidden potential.
So let's start with a number, 8. For a lot of modern computers, this is how many cores or individual processors it has. Just think of it like a team of 8 really skilled workers, all lined up and ready to get a job done. But now look at this number, 1. This is how many of those workers your typical program actually uses. That's right, just one worker is doing all the heavy lifting, while the other 7 are kind of just standing around. That is a ton of wasted power.
And that right there is the big problem. It's like having a whole construction crew ready to build a house, but only one person is actually laying bricks, while everybody else is on a coffee break. Yeah, the job will get done, but it's going to take way longer than it needs to.
So how do we get the whole team working? Well, we bring in a project manager. And in the world of programming, that manager is called OpenMP. It's an API, which is just a fancy way of saying it's a toolkit that lets our code talk to the computer hardware. And man, it knows exactly how to take a big job, break it up, and assign all those pieces to our waiting workers, all with just a few simple instructions. See, without OpenMP, a program is just a long to-do list for that one single worker. It's all sequential, line by line, one step at a time. It works, it's predictable, but it's slow. But watch what happens when we add just one little line of code, #pragmaomp parallel. This is what's called a compiler directive. Think of it as our project manager, OpenMP, yelling, "All right, team, let's go." And just like that, that single to-do list gets handed out to the entire team, and they all start working at the exact same time. It's kind of like magic. Okay, so how does this project manager actually organize all this potential chaos? It uses this really simple and elegant strategy called the fork-join model. It's the whole game plan for starting the work, doing it together, and then finishing up nice and clean. And this is exactly how it works. Your program starts with just one master thread. That's our project manager. When it hits that magic command, it forks, creating a whole team of worker threads. That part is called the parallel region, where everyone is working on the task at once. Then, once the job's done, they join back together. The team disbands, and our project manager carries on by itself. So simple, so efficient, and so powerful. So, what's this actually look like in the code? Well, think of it like a quick briefing for our construction crew. First, you need the instruction manual, right? In code, that's just including the OpenMP library. Next, you tell it how big your team is. Here, we're asking for 4 workers. Then you give the big go command, which we already know is #OMP parallel. And finally, you can give everyone a jersey number with a function like OMP get thread num, so each worker gets a unique ID and knows exactly which part of the job is theirs. Okay, so the team's assembled and ready to go. Now the big question is, what's the best way to split up the work? Do you give everyone a totally different job, or does everyone get the same job, just on a smaller piece of the project? Well, OpenMP gives us 2 main strategies here. On one hand, you've got functional parallelism. This is like having specialists. One worker handles audio, another handles graphics, different jobs happening at the same time. But on the other hand, you have data parallelism. This is where the whole team does the exact same job, just on different chunks of data. Imagine a giant pile of coins to count. You just split the pile evenly among the team. And honestly, the second approach is the most common one, and it's absolutely perfect for those really heavy, repetitive calculations. And that data parallelism approach is where you get the biggest bang for your buck for sure. So many programs spend most of their time stuck in loops, just repeating the same task over and over and over. With one simple command, #pragmaomp parallel 4, OpenMP just automatically splits all those loop repetitions among all your threads. It's like an instant productivity boost. But you know how it goes. With the whole team working at once, things can get a little tricky. If everyone is trying to write on the same blueprint at the same time, you're going to end up with chaos. And this is where managing your data becomes absolutely critical. The best way to think about this is with a simple analogy. A shared variable is like one big whiteboard for the whole team. Everybody can see it, and anybody can write on it, which is great for collaboration, but it can also lead to people accidentally writing over each other's work. A private variable, on the other hand, is like giving each team member their own personal notepad. Their work is safe, it's separate, and nobody else can mess with it. So what if you need a final combined result from everybody's private work? Well, that's where this clever process called reduction comes into play. It's pretty cool. Think of it like this. Each worker calculates a subtotal on their private notepad. Then, at the very end, the project manager comes by, collects all the notepads, and adds up all the subtotals into one grand total on the main whiteboard. It's safe, it's organized, and it's accurate.
So after this quick tour, what's the big idea? What should we really walk away with? Well, it's a huge shift in how we think about solving problems with computers. It's all about learning to think in parallel.
All right, let's just do a quick recap. We've seen that your CPU is really a team of workers, but most of the time we're only using one. We learned that OpenMP is like a project manager that uses a simple fork-join model to put that whole team to work. We know the easiest win is often parallelizing loops, and that the key to doing it right is carefully managing your data, deciding what's shared and what's private. This way of thinking powers everything from huge scientific simulations to the amazing graphics in your favorite video games.
And that brings us to one last thought. We are seriously reaching the physical limits of how fast we can make a single processor core. Moore's law is slowing down. So if we can't make one worker any faster, the only real way forward is to use more workers. And that leads to a really important question. In the future of computing, is learning to think in parallel no longer just a neat trick, but an essential non-negotiable skill?